At the COP26 in November last year, India committed to achieve net zero emissions by 2070, which is 2 decades later than COP26's target of 2050. 2070 indeed sounds too late, given how challenging climate change has become. Then what's the rationale behind the 2070 target? Why can't we just switch off the highly polluting coal and gas power plants and switch to renewable and green energy sources like solar and wind? In this video, we'll try to find answers to that, as to how practical it is to completely make the switch to renewable energy. And where does nuclear energy fit in the whole scheme of things? And also the technology, politics and economics behind this. Hello guys, I am Saurav and welcome to the Arc. So climate change refers to long-term shifts in temperatures and weather patterns caused due to human activities, especially burning of fossil fuels like coal, oil, gas, etc. Burning fossil fuels generates greenhouse gas emissions, which act like a blanket wrapped around the earth, trapping the sun's heat and rising temperatures. As a result of this, the earth is now 1.1 degree warmer than what it was in the late 1800s. The last decade, that is 2011 to 2020, was the warmest till date. The consequences of climate change include intense droughts, rising sea levels, water scarcity, melting of polar ice, catastrophic storms and cyclones, etc. So it's pretty serious. But how is non-fossil fuel or renewable energy going to solve this problem? According to estimates, power generation using fossil fuel like coal, gas and oil is the single largest contributor to global emissions, causing around 30% of our total carbon emissions. This is where renewable energy like solar and wind comes into picture. Renewable energy is energy from sources that are naturally replenishing but are flow limited. So if they are inexhaustible and don't emit greenhouse gases while generating energy, why haven't we completely switched to renewables? Let's find out. There are 3 factors that are driving this whole debate of switching to renewables. That is technology, politics and economics. We'll go through all 3 one by one. First, let's discuss technology. In 1955, Hoffman Electronics Semiconductor Division introduced photovoltaic products with only 2% efficiency, with a cost of around $1,785 per watt. But currently, the efficiency of solar panels has gone up to 22 to 26%. As the technology matured, the cost has gone down significantly. But then why not completely switch to renewables? Before getting into that, we need to first understand how does a typical power supply system work. There are 3 basic components of a power supply system, that is generation, transmission and distribution. Power is generated at generation units like coal, hydro, natural gas or solar or wind farms. This power is then sent to the transmission network after stepping the voltages up in step-up transformers so that it can travel long distances. Then from the transmission network, voltage is lowered by step-down transformers, and power is sent to the distribution network where voltage is further stepped down if required, and it finally reaches our homes at appropriate voltage and frequency. This entire system is an interconnected network of generating units, transformers, transmission and distribution lines, known as the electrical grid. This is how the high voltage transmission grid of India looks like. The grid is there to build redundancy and seamless supply of power. The grid is essential because power demand doesn't remain constant throughout the day. It varies with time. As and when demand increases or decreases, supply is adjusted in real time, usually at load dispatch centers that monitor these variations round the clock. Let's see how load varies in a typical day. If we plot the load demand in megawatt versus the time of day, the resultant curve would be called the load curve. Let's take this load curve example for a city in India. Here you can see load remains almost constant at around 10 megawatt during the night. But as day progresses, people wake up and start getting ready to leave for offices, and load increases gradually up to 50 megawatt. It then slowly decreases. It again increases as the sun starts to set, and lights get switched on between 6 pm to 8 pm. Load reaches a peak of around 60 megawatt and then decreases. Here the 10 megawatt is called the base load and 60 MW is called the peak load. Power generation plants are also categorized as base load and peak load plants. Coal and nuclear plants are generally base load plants because they have to operate continuously. Switching them on and off is very difficult. Natural gas and hydropower plants are usually peak load plants for their ability to quickly respond to peak demands. Now coming back to renewables. If we are to completely switch to solar and wind, they should be able to provide seamless supply of power throughout the day, as and when required. Here it gets a bit complicated. The one problem that plagues the renewable energy sources like solar and wind is reliability. Meaning we get solar energy only when the sun shines bright, and that is only during the day. Take this example of a solar power plant. Here power generation is plotted against the time of day. You can see the generation remains 0 up to 6 am until the sun rises. It slowly increases and reaches its peak between 12 to 3 pm and then decreases. But if we simply superimpose the load curve with solar power generation curve, we can see the peak supply and demand timings have a mismatch. This is where batteries come into picture. Because renewables like solar and wind depend on environmental factors, they can't generate constant power throughout the day. Hence, they require storage solutions, that is batteries. So when the sun shines bright and wind blows, energy can be stored for later use. But batteries aren't going to solve our problems entirely, which we'll discuss soon. Now let's move to the politics part. The earth is ours and it's everyone's responsibility to protect it. But is the responsibility same for all? This graphic represents greenhouse gas emissions by the countries as a percentage of total emissions. You can clearly see the top 3 greenhouse gas emitters, that is China, the US and the EU, emit 46% of the total emissions. Considering the severity of climate change, it's clear that these emissions need to go down. But should the responsibility be equal or equitable? Let me explain. The Western countries drove the Industrial Revolution in the 18th and 19th century, powering their industries by burning coal. It helped these countries develop, and as a result of economic growth, the lives of their citizens got better. But the rest of the world didn't see any Industrial Revolution until the second half of the 20th century, especially India and China. Now that the developing countries are growing economically, how can the extra financial burden of switching to renewables be justified? If we take the per capita emissions into account, the wealthier nations are the worst polluters. US and Saudi Arabia emit 17.6 metric tons of CO2 per capita, and China 6.4 metric tons per capita. India, on the other hand, emits only 1.7 metric tons per capita and accounts for 7.1% of global emissions. India's per capita emissions are 10 times lower than that of the US, 4 times lower than China, and 3 times lower than the EU. India has also committed to build capacity worth 450 gigawatts of renewable power by 2030 under the Paris Agreement and is on track to achieve it. In the last 6 years, India's renewable energy capacity has increased by 2.5 times, and only the solar energy capacity has increased by 13 times. Now, before moving forward, let's take a look at where we are at with respect to fossil fuel versus non-fossil fuel based power generation in different countries. In this graphic, you can see the energy mix of different countries as percentage of total generation capacity in terms of fossil fuel, nuclear and renewable energy sources. India has close to 4 lakh megawatt installed generation capacity. Out of this 4 lakh megawatt, around 60% comes from fossil fuel and nuclear. The rest 40% comes from non-fossil fuel or renewable sources. In case of France, most of the energy comes from nuclear and a very small amount from fossil fuel sources. In China, as you can see, electricity generation is divided almost equally between fossil fuel and non-fossil fuel sources. In case of the US, around 61% of the energy still comes from fossil fuel sources and the rest from the renewables. Now let's proceed towards the economics part. Purely in terms of generating 1 megawatt hour of electricity, cost of renewables has caught up, or have rather gone below the conventional power plants over the years. As technology improved and economies of scale kicked in, solar and wind energy are now the cheapest in terms of generating per unit of electricity. The cost of generating 1 megawatt hour of solar electricity has gone down to $40 in 2020 from $359 in 2009. Wind has come down from $139 to $41. Coal has remained almost same, around $110 for the same time period. And nuclear has gone up from $123 to $155. In 2020, this is how the cost per megawatt hour of energy looked for 4 major electricity generating sources. So if they are cheap and don't emit any greenhouse gases while generating energy, then why aren't we switching? Here comes the kryptonite of solar and wind energy, that is batteries. As we have discussed earlier, solar and wind are not reliable. To offset their environmental dependence, they need batteries to store energy when they generate excess electricity. But how much do these battery banks cost? The Victorian Big Battery Electricity Storage Facility in Australia, providing storage facility of 300 megawatt 450 megawatt hour, had an estimated cost of $160 million. If we are to completely replace fossil fuel sources with say solar energy, it would require a huge amount of money to offset the limitations of solar, to build redundancy in the form of large-scale battery storage. As we had discussed earlier, how solar electricity generation varies during the day, the variations are not limited to only during the day. It varies throughout the year as seasons change. Take a look at this table that has recorded the monthly mean hour solar radiation at Goa. You can clearly see how radiation reaches the maximum in the month of April and minimum in the month of July. So considering this data, if we are to provide seamless electricity to consumers using only solar, then we need to build capacity taking the minimum value that would be generated. That is, we have to assume the capacity of the solar farm corresponding to the lowest amount of energy generated to build redundancy, which means more battery storage than required and hence more cost. Also, energy can't be stored for longer periods, like more energy generated in summer months can't be stored to be utilized in winter months. For new solar and wind farms, the cost of new transmission lines and grid infrastructure that have to be built add to the total cost. So in conclusion, renewables like solar and wind can't completely replace our conventional power plants, but they can be paired with reliable baseload power plants. This is where nuclear energy comes into picture. Nuclear power plants are baseload plants that generate constant power throughout the year using the process of nuclear fission. But it's non-renewable because the most commonly used fuel in conventional nuclear fission power stations, that is uranium-235, is non-renewable. If it's non-renewable and limited in supply, then we should not consider it for our future energy needs, right? Not really, because nuclear fuel is extremely energy dense. For example, a 1-inch tall uranium pellet contains energy approximately equivalent to 17,000 cubic feet of natural gas, 120 gallons of oil, and 1 ton of coal. But how clean is nuclear energy? In 2014, the IPCC published a report harmonizing the CO2 equivalent of major electricity generation sources. As you can see in this graphic, coal of course is the most polluting one, emitting 820 grams CO2 per kilowatt hour generated. But the most interesting one is nuclear, emitting only 12 grams CO2 per kilowatt hour, even less than solar and almost same as wind. But this data makes no sense because solar and wind don't emit any CO2 into the atmosphere while generating energy. If we consider only the operational part, then yes, that's true. But if the entire life cycle of a power generation unit is considered, starting from mining of minerals to fabrication of materials and transportation and installation, then there will certainly be greenhouse emissions in the process. And batteries add significantly to solar and wind's carbon footprint, which requires mining of rare earth materials like copper, cobalt, iridium, etc. According to estimates, an average electric car battery weighs around half a ton. But to fabricate the same, it requires digging, moving, and processing of more than 250 ton worth of materials on Earth. Now coming back to nuclear, it has the highest capacity factor among all the energy sources. More the capacity factor, more reliable the plant is. But the one concern that daunts the policymakers to build more nuclear plants to produce clean and reliable energy is the safety concern. The first thought in anyone's mind that pops up hearing the word nuclear is Hiroshima, Nagasaki, and the nuclear bombs. Also, the three major events of accidents in nuclear reactors, that is 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima in 2011, can make anyone nervous. But the fact of the matter is, the official death count due to radioactive radiation post accidents in nuclear reactors remains 32 till date, with 31 people dying in Chernobyl and 1 in Fukushima. Here is a chart showing death rates per unit of electricity produced, which clearly shows nuclear to be one of the safest modes of electricity production. There is another concern with regards to nuclear waste. Nuclear waste is the fuel that has been used in the nuclear reactor once and which has to be safely disposed of. But as the energy density is very high, there isn't much waste anyway. According to estimates, all of the used fuel ever produced by the commercial nuclear industry in the US since the late 1950s would cover a whole football field to a height of approximately 10 yards. On the other hand, the amount of waste that we'll need to deal with at the end of the lifespan of solar panels, which is approximately 20 to 25 years, along with the used batteries, is going to be huge. Another huge factor that goes against solar and wind farms is the availability of land. Take a look. On the left, you can see the Desert Sunlight Solar Farm in California. It was commissioned in 2015 and it generates 550 megawatt of electricity. On the right, you can see the Diablo Canyon nuclear power plant in the same state of California. It was commissioned in 1985 and it is supposed to be decommissioned in 2025. It generates approximately 2256 megawatt of electricity. But the built-in area of Desert Sunlight Solar Farm is close to 4,000 acres. And for the Diablo Canyon, it's only 750 acres. So a 35-year-old nuclear plant generates 4 times the electricity than the solar farm, but with less than 1/5 of the land. The debate on the pros and cons of various renewable energy sources would go on and on as the technology improves and politics evolves over the years. But the fact of the matter is, without new nuclear plants, a large-scale decarbonization is not possible. In the long run, nuclear energy along with renewables like wind and solar are going to be the answers that we are searching for to deal with the climate change crisis. According to scientists, our best shot at dealing with climate change is by limiting global warming to 2, preferably 1.5 degrees Celsius compared to pre-industrial levels. In order to achieve that target, global carbon emissions should reach net zero around 2050. This would require huge funds and access to technology to make the switch to renewables, especially for developing nations. But who is going to fund that? According to estimates, India will need close to $10 trillion to meet its goal of net zero carbon emissions by 2070. There is no doubt that climate change is the single largest challenge for humanity right now, and all the countries are taking this climate change challenge quite seriously by ramping up renewable energy capacity and reducing dependence on fossil fuels. But the moot question here is, should the target of becoming carbon neutral by 2050 justified for all, because all the countries of the world didn't start their development journey together at the same time? I hope you liked the video. I hope to see you soon with a fresh and new video. Thank you.